This presentation is delivered by the Stanford Center for Professional Development.
Today, I want to finish up our discussion of Fourier series. In some sense, we don't really finish the discussion of Fourier series because it will always be a touchstone for reference for some of the other things that we do. But I want to finish up the discussion we started last time about using Fourier series to solve the heat equation. And then I want to talk about the transition from Fourier series to the Fourier transform and how one gets from the study of periodic phenomena to the study of non-periodic phenomena, which is exactly what the Fourier transform is concerned with, by means of a limiting process. All right, so that's where I want to finish up. But first, let me go back to the discussion we started last time about the heat equation. So this is the use of Fourier. This is a classic example, the classic example, one might say, of Fourier series, and it also shows, in a particular case, a very general principle that we will be seeing constantly throughout the course. That's really one of the reasons why I want to talk about it. So this is a Fourier series to solve the heat equation, one particular case of the heat equation. And I'll remind you what the setup is. We have a ring. We have a heated ring, like that, with an initial temperature distribution of, we're calling f of x. All right, so the initial temperature. So I'm thinking of x here as a spatial variable, a one-dimensional spatial variable, although the ring is sitting in two dimensions. So I can think of the ring, if I want, as an interval from 0 to 1 with the endpoints identified. At any rate, the important fact here is that since there is periodicity in space, since the ring goes round and round and round, the function f is periodic as a function of the spatial variable, the position on the ring. And we can normalize things to assume the period is 1. All right? So that's how Fourier series comes into the picture. So we take f to be periodic of period 1. All right? Then we let u of xt. Now the temperature is varying both in position and in time. The temperature changes as a function of time, and the temperature is different at different points along the ring. So I let u of xt be the temperature at a position x at time t. All right? Then u is also a function, is a periodic function in the spatial variable. U is a periodic function of x. So u xt is periodic in x. That is, u of x plus 1 t at any time t is u of x at the same instant of time, t. When t is fixed, it's periodic as a function of x. And the physical situation is described by the heat equation, which is also referred to as the diffusion equation and governs many similar processes that involve the diffusion of something through something else, through something medium. So heat through a region, charge through a wire is governed by this sort of equation. I mentioned these last time, holes through a semiconductor. It really has quite a variety of applications, and some of the techniques that we're talking about here, although they're specialized to this case, can be applied in various forms to many different situations. So you have the heat equation satisfied by it's a partial differential equation, so it relates the derivatives in time to the derivatives in x in space. So it says ut is equal to 1/2 uxx. Here I'm just choosing the constant. There's a constant on the right-hand side of the heat equation. I'm just choosing things so the constant is 1/2, just to simplify the calculations. So this is the first derivative with respect to time, and this is the second derivative with respect to x. All right. Now, because, I'll move over here. Because the function is periodic in x, we can expand it as a Fourier series, all right? So the rigor police are off duty. I'm assuming that everything converges here, and there's no question about writing down the sums. This is sort of a formal operation that whose particular, the particular manipulations that I'm going to do can be justified under reasonable assumptions, but that's not the point. The point is just to see how the techniques can be used to solve the equation. So I can write the function as a Fourier series. Now remember, it's periodic as a function of x, so the dependence on t is in the coefficients. K going from -infinity to infinity, that's, I'll call it c sub k of t times the periodic term, e to the 2 pi I kx. I'm assuming period 1, okay? That's the basic assumption. Or rather, that follows from periodicity. You can expand it as a Fourier series. That's how Fourier series get into the picture. Then you plug into the equation We did this last time. I'm just reminding you of the setup. Plug into the heat equation and equate coefficients. And you get an ordinary differential equation for the C's, for the coefficients. The C's are the unknowns there, all right? So you get this equation. You get ck prime of t is equal to minus 2 pi squared k squared times ck of t. All right? That's a simple ordinary differential equation, and we know how to solve it. So it's a simple ODE. And its solution is ck of t is e to the minus, is the initial condition, ck at 0, times e to the minus 2 pi squared k squared t. That's easy. That is easy. And this, I think, is where we got to last time. All right? Now, what is the initial condition? All right? I haven't brought in the initial temperature here, but here's where it comes in. So what is ck of 0? All right, ck depends on time. What is the initial condition? Well, we can see it, actually. Remember, u of xt is the sum from k equals minus infinity to infinity, ck of t times e to the 2 pi I kx. So what happens at t equals 0? At t equals 0, this is the initial temperature distribution. All right? U at x, any position on the ring at time 0, is f of x. You give it some initial distribution of heat. Okay? So that says that f of x is u of x0. That's the sum from, if I plug into the series, sum from minus infinity to infinity of ck of 0 e to the 2 pi I kx. Now, we have eyes if only we but see. What does this say? F is a periodic function. This is an expansion of f in terms of the harmonics, in terms of the building blocks, e to the 2 pi I kx. What are the coefficients of c? What are the coefficients ck of t in terms of f? What is ck in terms of f? ck of 0 in terms of f? Pardon me? It's the Fourier coefficient of f. All right? So this must be the Fourier series of f. That is to say, i.e., ck of 0 is just the kth Fourier coefficient of f, f hat of k. All right? You know, say, we have eyes if only we but see. What I meant by that provocative statement is you have to be able to go from the function to the series, but you also have to be able to go from the series to the function. All right? So here's the function, here's the series. You have to be able to relate, say this is the series for a function, so it must be that these coefficients are the Fourier coefficients for the function. All right? You're used to having problems like, here's the function, compute the Fourier coefficients. All right, well, in some sense, the Fourier coefficients are already computed here, so relate them to the function. All right, let's write that down. Let's write that down. That is, when I say write that down, what I mean is, what does the solution look like? So u of xt, the temperature, this is already very impressive. The temperature at any time t, at any position x on the circle is f hat of k times e to the minus 2 pi squared k squared t times e to the 2 pi I kx. You can see from this the dependence on time and the dependence on x. It's a complicated expression, but it's pretty impressive. All right, you have found that given an initial temperature distribution, this is the formula for how the heat, for the temperature at any point x on the ring at any time t. You can already draw some conclusions from this, namely as t tends to plus infinity, what happens to the temperature? Goes to 0. All right. As t tends to infinity, this term is damping out. Now, see, there's a cute little thing to observe here. This is an exponential e to the minus 2 pi squared k squared t. Now, k is going from minus infinity to infinity. All right. k is both positive and negative here. But k appears here squared. So k squared is always positive. So this multiply minus 2 pi squared k squared, this number is always positive, so minus it is always negative. It's e to the minus something as t is tending to infinity. All right? That's a little sort of check on consistency there. So as t tends to 0, this is just an observation. As t tends to infinity, u of x t tends to 0 at for any value of x. All right? So the ring is cooling off eventually. All right, now, this is perfectly fine, actually. This is a perfectly fine way of writing the solution for reasons which I will explain, and for reasons which we will see oftentimes in the course. I want to work with this a little bit more, and I want to write the equation in a different form. And this was exactly the sort of thing I had to do on homework. Although on homework, it turned out even a little bit simpler than this. It may not have seemed it, but it did. I want to write this sum differently. I mean, again, we've solved the problem in the sense that we have found a formula for the temperature at any point x on the circle at any time t. All I'm saying is there's an alternate way of writing it that itself is very revealing and, in fact, has consequences that go beyond the particular problem that we're studying. All right, so to do that, I want to bring back the formula for the Fourier coefficient. So I want to write f hat of k. I want to use the explicit formula as an integral. So I want to use f hat of k is the integral from 0 to 1. Now, I've already used x as the variable here, so the variable for integration, I'll use something else, like I'll just use a y. It doesn't matter what I call it as long as I'm consistent. So I'll write this as e to the minus 2 pi I k y f of y dy. All right, that's a formula for the Fourier coefficient. And plug that in to the formula for the solution. So I get u of xt is the sum, again, from k going from minus infinity to infinity, of this integral, is the integral from 0 to 1, e to the minus 2 pi I ky f of y dy, e to the minus 2 pi squared k squared t, e to the 2 pi I k x. That's why you have to do this on a big blackboard with big chalk. All right, now I'm going to combine terms and swap the integral and the sum. Again, the rigor police are off duty. And so interchanging integration and summation is something we can do with impunity. Mathematicians can do it with impunity also, but it takes them 3 years of graduate courses before they really feel good about it. We don't have the time for that. So this is, I'm going to swap the integral and the sum. So this is the integral from 0 to 1 of the sum, k going from minus infinity to infinity. So let me put the terms together like this. E to the minus 2 pi I k y, e to the 2 pi I k x, e to the minus, I'm putting all the terms together that get summed, e to the minus 2 pi squared k squared t. Those terms all get summed, and then what stays on the outside is f of y dy. All right, I haven't done anything there. I've just rearranged things, and I've swapped integration and summation. And I'll do one more step. This integral from 0 to 1, sum from k going from minus infinity to infinity. I'll put these two terms together because they're both got i's in them. E to the 2 pi I k x minus y, e to the minus 2 pi squared k squared t, f of y dy. Okay, like I say, I haven't done anything really except rearrange terms. I've rearranged terms this way because I know what's going to happen, or rather I know how to finish the discussion, because I know what years of bitter experience taught the people before me, finally. That is, that sum deserves to be singled out for special attention and deserves to be given its own special name. So I'm going to write, say, g of xt to be this sum, k going from minus infinity to infinity, e to the 2 pi I x e to the minus 2 pi squared k squared t. Okay? So this is actually g of x minus y, comma, t. That is, the integral, the solution appears in this form. Pardon me? Kx, thank you. 2 pi I kx. Okay? All right. So the solution u appears in the following form. If I just use that as a shorthand notation, the solution looks like this. U of xt is the integral from 0 to 1, g of x minus y, comma t, f of y, dy. All right, and that's all I want to. I'm not going to do anything else. I promise you. I won't do any more rearranging. I won't do any more fiddling around. That's how I'm going to write the solution. Now, for those of you who've seen this and you actually saw it, you saw a similar sort of thing on the homework problem. This expresses. So this is an important statement that I'm about to make. Drum roll. All right. This expresses the solution. The general solution at any time x, any time t, as the convolution of the initial condition at time 0 with this kernel. All right? This expresses u xt as the convolution of f of x, f of y, doesn't matter, f of x with what's called the heat kernel g of xt. So there's a lot of terms there that we haven't heard before, although you may have heard in different contexts the term convolution, which we were going to be hearing all the time. And in this special case, you also call this the heat kernel. You also call this the fundamental solution, or the Green's function for the heat equation. So I will just, without saying really anything more, just to introduce you to the terminology, you call g of xt, has a variety of names. That function that I wrote down, g of xt, is called variously the heat kernel. That is, it's a kernel for the heat equation. You use the word kernel often when it appears underneath an integral in the context of convolution like this. Heat kernel is also called the fundamental solution of the heat equation. And it's also called Green's function for the heat equation. All right, now let me just ask, just take a survey out there. First of all, who's studied this problem before? Who studied the problem of heat flow sort of this way with Fourier series? All right, so a couple people, but not that many, actually. All right, in what class or what context? I'm just curious.
131.
Oh, is that right? Okay. And they did it more or less like this?
Pretty similar.
Yeah. I mean, they probably worried about certain things like convergence and things like that, right? You know, but screw them. Oh, excuse me. All right. And how about this terminology? So have you heard this terminology, the heat kernel, the fundamental solution of the Green's function? Most people who've taken many physics courses have often heard the term Green's function for differential equations and things like that. You may have seen that. And I'm not going to make a big deal out of it, but again, it's sort of an indication of the kind of techniques and the kind of ideas that come up in this class you see everywhere. All right? For us, the reason why I went through the solution, all right, and the reason why I wrote the solution this way was to bring up this idea of convolution. All right. Convolution is a very general operation. People in electrical engineering have seen it very, very early on in their classes on signals and systems. We are going to see it in all sorts of different contexts, not always in terms of not always associated with differential equations, but sometimes associated with differential equations. And it is the kind of thing that comes up. All right. The fact that you could write a solution as the convolution of two functions, in this case, the initial distribution of heat and the special function that's associated with the equation. All right. I'm not going to say any more about it now. I'm not going to even give you the general definition of convolution. But all I wanted to do by showing you this was it comes up in a very, in retrospect, in a natural way. It's the sort of thing you should expect to see. All right. It's one of the things, you know, when you're working with any problem almost that has to do with Fourier analysis, it should not surprise you to see convolution coming into the picture somehow. All right? And this is an example of that. On the homework, you had another example of it. All right? You had an example of another celebrated problem in mathematical physics, the so-called Dirichlet problem, where, again, the solution ultimately could be written as convolution. There, the nice thing was that you actually got a closed-form expression for essentially the Green's function of the fundamental solution for that problem. All right? The Poisson kernel is actually a closed-form expression. There's no similar closed-form expression here. All right? You can't do anything more with this function. All right? It is what it is. It's just this infinite sum. For the problem you had in homework, again, you get an infinite sum that comes in, but it collapses because it's a geometric series. All right? And you get a nice closed-form expression for the Poisson kernel. But you know, in principle, the principles that are operating here are very similar for the two problems. All right? And again, it's sort of a fact that took a long time to sort out that when you have partial differential equations, which govern many physical phenomena, the solutions often appear in the form of convolution with a special solution, so-called fundamental solution, with the initial conditions, with the initial data. It's something you should expect to see. This is a pretty big major secret of the universe, all right? I mean, so, you know, take that to heart. You'll see this. Be afraid, be very afraid. No, show no fear. All right, it's what you should expect. Okay. And with that, pretty impressive. And as I say, this is also part of your intellectual heritage. All right, you should know this solution, know this approach to the problem. It's a very famous problem. It had all sorts of far-reaching consequences. It should be part of your soul. Okay. All right. But with that, we bid adieu to Fourier series. Although, as I say, we'll come back to it from time to time. And actually, maybe it's not right to say we bid adieu to it, because right now what I want to do is talk about the transition from Fourier series to Fourier transforms. All right? And that is the transition from periodic phenomena to non-periodic phenomena. So I want to make a transition from Fourier series to Fourier transforms. All right? And this is the transition from periodic phenomena to non-periodic phenomena. All right? Now, I've said before, and you'll hear me say it again, we have to make a lot of choices in this class, and choices for how to cover the material. This is not the only way of doing it, all right? In many treatments of the Fourier transform, you don't do it this way. That is, you don't start with Fourier series and then try to make the transition to Fourier transforms, all right? It's just the Fourier transform is presented as sort of a deus ex machina, you know, God in the machine or whatever. It's just there, you know, and it's justified by its many uses, all right, and its important applications. And that's fine, and that's quite justifiable. I didn't want to do that because I wanted to show you the basic phenomena associated with periodicity. It's an important enough topic, and I wanted you to sort of have some of those things. I wanted to try to cultivate your intuition a little bit for those sorts of ideas. But you don't have to do it this way, all right? If you look at Bracewell's book, which is a very common and popular book that's been used for this course. Ron Bracewell just passed away, actually, was a professor in the electrical engineering department here for many, many years. His book starts out with the Fourier transform, with no mention of Fourier series, and then later on, they actually recover some of the ideas of Fourier series based on the Fourier transform. And you can do that. But that's a choice, all right? And I have made a different choice. That's all that's involved here. Now, the transition from periodic to non-periodic phenomena, and the way we're going to accomplish that is to view a non-periodic phenomenon as the limiting case of a periodic phenomenon as the period tends to infinity. All right? So we'll do this by viewing non-periodic function, I won't say phenomena, so non-periodic function, as sort of a limiting case of the periodic phenomena, periodic function as the period tends to infinity. Period tends to infinity. Okay? It's a little tricky to do this, actually. It's not completely, I mean, it doesn't just doesn't happen completely automatically. All right? It takes a little work. All right? It's not a completely automatic process. Now, the other thing to realize is there are actually I'll do it over here. There are actually two aspects to this. All right, so once again, let me remind you the Fourier case, the Fourier series case. All right, the two aspects of the Fourier transform, really. Two aspects, there's analysis and synthesis. So the analysis is the Fourier series is forming, so again, if f of t is periodic, all right, then you have the Fourier coefficients, the integral from 0 to 1 e to the minus 2 pi I k x f of, or kt f of t dt. All right, that's analysis, right? That's analyzing. That's analyzing the function, the signal, into its constituent components, figuring out how much each complex exponential contributes to the whole by this much, this amount. Then there's synthesis. The synthesis is writing the series, all right? Recovering the function from its constituent components. Sum from minus infinity to infinity f hat of k e to the 2 pi I k t. So that's synthesis. All right? And both of those things generalize to the Fourier transform. The Fourier transform is the generalization of the Fourier coefficient. The inverse Fourier transform is the generalization of the Fourier series. Fourier transform is a generalization, or the limiting case, if you want to think about it that way, generalization that is limiting case in the sense that I'm talking about here is the period tends to infinity case of the Fourier coefficient. So that's the analysis, decomposing a signal into its constituent parts. The inverse Fourier transform is a generalization or the limiting case of the Fourier series. Is the limiting case of the Fourier series. That's the synthesis part of the equation. All right, synthesis part of the discussion. Okay, now, so how do I set this up in order to take a limit? All right, so I keep saying that it's the limiting case as the period tends to infinity. So that means I have to give you the setup for Fourier series, for Fourier coefficients and for Fourier series when the period is not 1, but the period is some other number, capital T, that I can let tend to infinity. So we need to set up when, say, f of t is periodic of period t. All right, and then ultimately I want to let t tend to infinity. I want to let t tend to infinity. Okay? All right, so how do I do this? Well, you read about this, I hope, I expect. And let me tell you what the formulas are. It's not hard. The building blocks for a signal of period t are complex exponentials of period t, so that's e to the 2 pi I k t over t. Or I'm actually going to write it a little bit differently. I'm going to write it as e to the 2 pi I t k over t. Doesn't matter. I just switched the parentheses there. All right, same thing. These are periodic of period capital T. All right? And the Fourier and the corresponding Fourier series put it down here. The Fourier series are of the form ck, k going from minus infinity to infinity, c sub k, e to the 2 pi I k x kt k, I don't know, write like this, k over t t, or k little t over capital T. I'm going to write it like that for reasons you'll see in just a second. All right? That's what the Fourier series looks like. What are the coefficients? Well, again, I mean, one can repeat all the arguments that we did when we were working with functions of period 1, or actually you can use the results for the period 1 case to derive the general result. At any rate, what you find is c sub k is given by 1 over t times the integral from 0 to t of e to the minus 2 pi I k over t, little t, f of t, dt. Okay? Did I say here anywhere that little f is periodic of period t? I guess I didn't say that, so sorry, let me say it now. F of t here is the given signal, so I'm assuming it is periodic of period capital T. So f of t, periodic of period capital T. Okay? That's the formula for the kth Fourier coefficient when the function has period capital T. And actually you use this again in a homework problem. Okay, now one other thing. I want to write this a little bit differently again for reasons which you will see in a moment, because I have in mind taking a limit here as capital T tends to infinity. I can also write this. The function is periodic of period T. Doesn't matter what interval you integrate over. If I know the function on an interval of length T, I know it everywhere. So I can also write this formula, and again, this is discussed in a little bit more detail in the notes. I can also write the formula as, instead of integrating from 0 to T, I can integrate from minus T over 2 to T over 2, a symmetric interval from negative to positive. Same thing, e to the minus 2 pi I k over capital T, t, f of t, dt. Okay, fine. Now, all right, so this is really no different than what I've done before, except I've written things a little bit more generally. Instead of a function of period 1, I have a function of period capital T. All right, but the formula for the Fourier coefficient is perfectly analogous to what I had before, and the formula for the Fourier series is perfectly analogous to what I had before. So again, that's analysis, that's synthesis. All right, you analyze the function into its constituent parts, then you synthesize it by forming the corresponding sum. All right, now, I want to point something out here that's very interesting. How would you draw a picture of the spectrum for these cases? All right, what's a picture of these things? All right, what's the picture of this? Picture of the spectrum. Picture on the frequency side. Picture of the spectrum of frequencies. All right. Well, in the case of period 1, let's take period 1. All right. Then the Fourier coefficients are given by the usual formula that we had before, and you might draw the spectrum like this. There's a coefficient at 0. That's the 0th coefficient, C0. Then there's a coefficient. Well, let's see. 0, 1, 2. I have frequencies at all the integers, -1, -2, and so on, 3, -3. And they're spaced, so to speak, the harmonics, the frequencies are spaced one apart. Here is like absolute value of C0. Here's absolute value of C1. Here's, I say absolute value because they're actually complex numbers. The coefficients are complex numbers, so I can't actually plot them. But I can get a picture of the spectrum by plotting the absolute value. Here's absolute value of C2. Here's absolute value of C3, whatever it is, all right? And what do I get on the negative side? What do I get on the negative side? On the negative side, I get the same absolute values because of the symmetry relation C minus K is equal to CK bar. So the absolute value of C minus K is the magnitude of C minus K is the magnitude of CK bar, and the magnitude of a conjugate of a complex number is the same thing as the magnitude of the number. So this is also the magnitude of CK. So the picture is the same on the left. So this is the magnitude of C minus 1, the magnitude of C minus 2, the magnitude of C3, whatever. Magnitude of C minus 3, whatever it looks like. All right, that's the picture. And in fact, if you've ever worked with a spectrum analyzer, and if I have the chance, I'm going to bring one into class, you see pictures like this. You see a signal and you see these bars that are at the different frequencies. Okay? All right, now, the important thing here is, the reason I mentioned this, is they're spaced 1 apart. All right? Because of period 1, the frequencies are also 1 apart. 1, 2, 3, and so on and so on. Now, what about for a function of period t? So the spacing here, the spacing of the frequencies is 1. Is 1. The spacing of the frequencies is 1. They're 1 apart. Okay? If you were going to draw the picture. Now, what about if you have period t? Okay? What about if I have period t? Well, what is the picture there? The picture is like this. Okay? The Fourier series looks like this. The Fourier series for a function of period t looks like the sum from minus infinity to infinity, c sub k e to the 2 pi I k over t times t. So the harmonics, they're indexed by k, but they're periodic at period t, so really the harmonic you're interested in is, in some sense, tagged by k over capital T. All right? So 0, 1 over t, 2 over t, 3 over t, minus 1 over t, minus 2 over t, minus 3 over t, and so on. All right? So if you were to draw a picture of the spectrum that would correspond to a series that looked like this, you would draw a picture that went something like this. You would draw 0. So this is now period. So this is for period 1. For period t, you would draw the first harmonic is sort of at 1 over t. The second harmonic is 2 over t. The third harmonic is 3 over t, and so on and so on. All right? Then it's minus 1 over t, minus 1 over t, minus 2 over t, and so on. The spacing is 1 over t apart. And here's the 0th Fourier coefficient. Here's the first Fourier coefficient. Here's the second Fourier coefficient. Here's the third Fourier coefficient. The ones on the negative, corresponding to the negative frequencies, have the same. And when I say here's the first, here's the second, here's the third, I mean the magnitude. All right, because again, you can't plot complex numbers. You're just plotting the magnitudes. And on the left, I have the same picture because it's symmetric. So it's like this, like that, and so on. Minus 3 over t, and so on. All right, they're spaced 1 over t apart. So the spectrum has spacing 1 over t. All right. Now, this is another example. Remember very on when I first talked about frequency and wavelength, and talk about the inverse relationship or the reciprocal relationship between frequency and wavelength, very first day of class. That's something you saw a long time ago. This is our second related example of an inverse or reciprocal relationship between, in this case, I'm going to say the two domains, how the function appears in the time domain and how the function appears in the frequency domain, how it is as a function of time and how it is in terms of its constituent frequency parts. If the period is t, then the spacing of the frequencies is 1 over t. All right? There's a reciprocal relationship here between the period and the frequencies. Between the period, that's often in what's happening to the function in time, the time, or what's sometimes referred to as the time domain of the function, and the frequencies, between the period and the frequencies. Or viewing the function in the frequency domain, viewing it in terms of its constituent parts. The reciprocal relation, so period t means frequency spacing of the frequencies 1 over t. Frequency spaced 1 over t apart. Okay? All right. I didn't say anything about the size of t here, but that's a general reciprocal relationship between the two domains. And again, it's just something you're going to see throughout this course, or a reciprocal relationship between the two views of the function. All right? And that reciprocity is exactly mediated by Fourier techniques, Fourier series in this case, or very soon, the Fourier transform. But it's, again, it's the kind of thing, this is the sort of intuition you have to start to develop. You're viewing the function one way, you expect certain things. You view the function in the other domain, you expect the reciprocal phenomenon. Now, all right. So in particular, if t is less than 1, if t is less than 1, then 1 over t is bigger than 1. So t less than 1, so a function which repeats more frequently than once a second, implies larger or smaller spacing than 1. Implies 1 over t is bigger than 1, so the spacing is larger. Spacing, 1 over t is bigger than 1. Spacing bigger than 0. Bigger than 1. All right? The spectrum is spread out. All right? If t is bigger than 1, if you have a long period, the spectrum is compressed. The spacing is 1 over t. 1 over t is less than 1. All right? So the spacing in the spectrum, is squeezed, compressed. All right? In particular, as capital T is going to infinity, which is the case ultimately I want to deal with, the spectrum is getting more and more, the spacing of the spectrum is smaller and smaller. The frequencies are getting closer and closer together. 1 over t, 2 over t, 3 over t, 4 over t, they're getting closer and closer. 1 over t is getting smaller and smaller, and they're getting closer together. As t tends to infinity, the spectrum becomes sort of continuous. I'm going to make this more precise, or rather I'm going to make this more explicit, if not more precise, in just a minute. All right? But the idea is the spectrum is getting closer, the frequencies are getting spaced closer and closer together, because the spacing is 1 over t. Spacing is 1 over t, and if t is tending to infinity, the spacing is tending to 0. That's what I mean by the fact the spectrum is getting continuous. All right? So the spectrum is getting squeezed. Okay, now, what's the formula for the coefficient here, once again? Well, let me just start now. Now, one thing at a time. So once again, let me write down the formula for the coefficient. Ck is 1 over t. This is the definition for the Fourier coefficient when the function has period t. So I'm going to integrate from minus t over 2 to t over 2 e to the minus 2 pi I k over t little t f of t dt. Okay? All right. Now, I want to let t tend to infinity here. All right, and use this as a way of passing from periodic to non-periodic phenomena. Okay, and use this pass from periodic to non-periodic. But as I say, it's not quite straightforward. And let me tell you why. I can't just take the limit as t tends to infinity there and the Fourier transform pop out of that. It doesn't work. All right? You can't just let t tend to infinity and get the Fourier transform. You have to tickle it a little bit. And actually, let me leave this picture up on the board and show, and show over here. All right? Let me tell you what the setup is going to be and what I want to do. So imagine I have some function which is not periodic. But suppose it's finite in extent. So suppose f of t looks like this. Some function, on some interval going from a to b. All right, and it's 0 beyond less than a and bigger than b. All right, so that's my function. So I take some big number, t, and I periodize this, say bigger than, so the minus t over 2 is less than a and plus t over 2 is bigger than b. All right, so here's my function. It's 0, less than a, it's 0, bigger than b. I take some, and I want to approximate this thing by, I want to imagine this is a periodic function. So I take some big period beyond where the function is 0, and I periodize it to be period t. All right? Take a big T and periodize to have period t. Okay, fine. Now, write down the formula for the Fourier coefficient. All right, so imagine, if the function here were fixed, if that's all I'm worried about, and let t go to infinity, then I'm sort of approximating that non-periodic phenomena by a periodic phenomena with a very big period. All right? That's going to be my goal. But the problem is, and I want to see what happens to the Fourier coefficient. So write down c sub k. The Fourier coefficient looks like this. C sub k is 1 over t, the integral from minus t over 2 to t over 2, e to the minus 2 pi I k over t, little t, f of t, dt. Okay? That's the case Fourier coefficient. But now, f is 0, less than a, and bigger than b. And those numbers are fixed. All right? Those are sort of given to us. So this is equal to 1 over t times the integral from a to b of e to the minus 2 pi I k over t, little t, f of t, dt. Right? Because the function f, I'm assuming, is 0, less than a, and bigger than b. Okay? Now, this integral in absolute value is going to be bounded. The integral from a to b of e to the minus, in absolute value, e to the minus 2 pi I k over t, little t, f of t, dt. The absolute value of the integral is less than the integral of the absolute value. This is less than or equal to the integral from a to b, the integral of the complex, the absolute value of the complex exponential, which is 1, times the function dt. The absolute value of a complex exponential is 1. I'm almost there. Almost there. So this is just equal to the integral of this absolute value. You'll see why I'm doing this in just a second. Really, really, really. This is equal to the integral from a to b, f of t dt, because the absolute value of the complex exponential is just 1. That's a fixed number. It's like m, you know. All right? Okay, so what does that say about the Fourier coefficient? All right? Watch what I did here. I just wrote down the formula for the kth Fourier coefficient. What I want to see is I want to convince you there's a little bit of problem with directly letting t tend to infinity. If I directly let t tend to infinity, everything's going to die. Here's the kth Fourier coefficient. It's 1 over t times this integral. What about that integral? That integral is that integral, and this integral in absolute value is bounded. Let's say goodbye to this drawing now. So this says that in absolute value, c sub k is less than or equal to 1 over t times m for all k. All right? So as t tends to infinity, c sub k tends to 0. The Fourier coefficients die. All right? So I had this wonderful idea. I said I'm going to approximate a non-periodic phenomenon by a periodic phenomenon, a very large period, and I'm going to let the period tend to infinity. Sounds great. All right? Sounds like a very natural thing to do. I write down the formula for the Fourier series. Great. I got these coefficients for the Fourier series. Great. I'm going to let t tend to infinity. Great. The coefficients are going to tend to 0. Not great. I'm not going to get a formula that's going to help me as t tends to infinity. Not great. All right. I think I have to quit right now. Tomorrow, on Friday, I will tell you how to save this. All right? In a very nice, easy way that's going to lead to everything. All right.